Now we see how ChatGPT understands context. I mean, it's been said a lot of times that computer doesn't understand our language, our human language. So, but then we can translate, we can convert our language into a language that computer understands, and that involves numbers and all that. And that leads to the idea of embeddings and the rest of ideas related to that. So how ChatGPT understands context and our learning objectives here include the following. Now, by the end of this lesson, you'll be able to explain what context means in large language models, then understand why text must be converted into tokens, explain token relationships, understand embeddings as vector representations of language, and compute semantic similarity using cosine similarity. I mean, we've done a lot of these things previously, but I mean, we just want to add more context to the whole thing. Then understand how ChatGPT builds contextual understanding and apply these ideas using Python. So why this lesson matters? One of the most fascinating abilities of ChatGPT is its capacity to answer questions while maintaining context throughout a conversation. So surprisingly, ChatGPT does not understand English in the same way humans do. I mean, I've said that a lot. Instead, it performs billions of mathematical operations on numerical representations of language. So, so ChatGPT, we are able to communicate with ChatGPT, and it is able to communicate with us because we are able to represent language numerically like that. So every sentence you type is transformed into tokens, and then the tokens are given numerical vectors or what you call embeddings, and then mathematical relationships are established and their probability calculations. Understanding this pipeline is essential for understanding modern artificial intelligence. Now, what is the context here? Context, we're talking about how ChatGPT understands context, right? Context is the surrounding information that helps determine the meaning of a word, a phrase, or a sentence. So, for instance, if I say bank, so I need to give you the context because it can be river bank and it can be bank account, right? So, if I say that I'm standing I stood at the bank for 5 minutes before diving into the river. So, well, that is ambiguous, but it is easier to think of the bank as the river bank than the bank where you transact money. But or if I say I withdrew some money from the bank, so that is clear. And it is the fact that it is from bank where monetary transactions are carried out. So context is the surrounding information that helps determine the meaning of a word, phrase, or sentence. Humans naturally use context when interpreting language. So the same word can have multiple meanings depending on the surrounding words. Oh, okay. I mean, there's the bank thing here even. So in example one, consider the sentence, I went to the bank. Now, what does bank mean here? Without additional information, we cannot determine whether the speaker means a financial institution, the side of a river, or a place where aircraft tilt during flight. So now consider I went to the bank to deposit my salary. Here, the surrounding words deposit and salary strongly indicate that bank refers to a financial institution. Now consider we sat on the bank watching the river flow. Now, bank refers to the edge of a river because we're talking about the river flow right there. So it means context is more than nearby words. So, I mean, there we see context can be about nearby words, but it is even more than that because context includes previous words, previous sentences, previous paragraphs, the overall topic, relationships between ideas. For example, John bought a laptop. He loves using it for programming. The word it clearly refers to laptop, not John. All right. John bought a laptop. He refers to John, but using it, he loves using it. It there is the laptop for programming. So human resolve this automatically. So we already know all this because we understand our language. So ChatGPT performs mathematical computations to infer this relationship. That so for ChatGPT to understand that it refers to laptop, it has to do some mathematical computation. Now, why does context matter? So, without context, language becomes highly ambiguous. Consider these examples. The bat flew into the cave, meaning of the ambiguous word, flying mammal. So the bat there. So it could be, it could be bat for playing sports. So he swung the bat and hit a home run. That is the sports equipment there. The mouse ate the cheese. Of course, that mouse there is an animal. Move the mouse to click the button. That is a computer device. So context actually moves ambiguity. Now, context in conversations now. Suppose the conversation proceeds as follows. You have a user, my favorite programming language is Python, and later the user says, can you recommend a good book for it? All right. So my favorite programming language is Python. That has gone well ahead. Then can you recommend a book for it? So humans know that it refers to Python. Similarly, ChatGPT analyzes previous tokens in the conversation and determines that it most likely refers to Python, but that has to be done mathematically. So let's talk about the mathematical view of context now. Now, when a sequence of suppose the sequence of tokens is T1, T2, T3, and all of that. So whatever you feed into ChatGPT, for instance, that's your prompt. So the prompt is broken down into tokens. So let's say you have n tokens, like from T1 to T2 to T3 up to Tn. When predicting the next token, ChatGPT uses the probability to say the token at this point, at the next time point. So you have to get the token at the next time point, given tokens at all the other points up till now. So we're T1, T2 up to Tn are all previous tokens in the context. Tn plus 1 is the next token to be predicted, while P, probability function denotes a conditional probability. Now, rather than understanding meaning symbolically, the model learns statistical relationships between tokens from massive amounts of training data. So some key takeaways, they're talking about the idea of context. First of all, we see that context provides meaning. And then the same word can have different meanings in different contexts. Like when we talk about bat, it can be bat for playing sports, it can be bat, the animal, the mammal, and it can be, when we talk about bank, it can be river bank, and it can be bank where we deal with money. Then ChatGPT determines meaning mathematically rather than symbolically. I mean, that what is normal to humans. ChatGPT needs mathematics to get it. Every prediction depends on previously observed tokens. So previously observed tokens determine what's going to happen next. And then context is the foundation of modern large language models. So context really matters. Now, why computers cannot read text directly? I mean, we've established this for amply. So, unlike humans, computers do not understand words or grammar or meaning. A computer only understands numbers. Therefore, before ChatGPT can process any sentence, every piece of text must first be converted into numerical form. So this conversion happens in several stages. So you have the text, that's your prompt, broken down into tokens, and each token is given an ID, and then you have embeddings by converting them into vectors, and then have your neural network. So each stage transforms the text into a mathematical representation that the model can manipulate. Example, suppose the input is artificial intelligence is transforming education, if that's what you imputed into the computer. A human immediately understands the sentence, but a computer cannot. Instead, the sentence might first become artificial with token ID 11689, intelligence 4456, is 2003, transforming 17903, education 2495, full stop 1012. The actual numbers vary depending on the tokenizer used by the model. So the tokenizer gives token ID to the tokens, to the words broken down. So these numbers have no mathematical meaning by themselves. They are simply identifiers, much like student identity number. So you want to identify students in a large school. So the identity number is what helps you. Now, why not use ASCII? So one might wonder why we cannot simply use ASCII or Unicode values. For example, for cat, we can just have C67A97 T116. However, ASCII only represents characters. So ASCII is for characters. It does not represent meaning. So notice that cat, dog, and car have completely unrelated ASCII values, even though cat and dog are much more similar in meaning than cat and car. Therefore, modern language models require a much richer representation. And then that takes us from the idea of characters to meaning. Instead of just working with characters, we now go to meaning. So instead of using character codes, language models convert text into tokens and later into embeddings. So this allows similar words to have similar mathematical representations. For example, you have cat, dog, lion, tiger. Will eventually obtain vectors that are close together in embedding space because they represent related concepts. So cat, dog, lion, tiger, they're animals and they are like of the cat or dog family, like that. Meanwhile, if you talk about laptop, banana, and volcano, they will occupy very different regions of that space because they are so unrelated. Then every conversation is mathematics in short. So suppose you type explain machine learning. Internally, the model performs something similar to explain machine learning. So instead of saying explain machine learning, it converts explain is 7132, machine is 3697, learning is 4083, and that number can vary depending on the tokenizer used in your model. So these integers are then transformed into vectors such as x1, x2, x3. The neural network never works directly with the original words because it doesn't understand. It only processes vectors. And that is why embedding, tokenization and embedding are necessary for ChatGPT, for us to converse with machine. Now, why numbers matter? Representing language as numbers enables the model to perform operations such as matrix multiplication, vector addition, dot product, cosine similarity, probability estimation, and optimization using gradient descent. Now, without numerical representations, none of the modern deep learning would be possible. So we need numerical representation for deep learning to be possible, for artificial intelligence to be possible. So we're talking about mathematical representation. Now, suppose the sentence contains n tokens, say T1, T2 up to Tn. The tokenizer converts this into token IDs I1, I2 up to In. Each token ID is then mapped to an embedding vector E1, E2 up to En. Now, in case all this idea of embedding and everything is confusing to you, you may want to check my playlist on abstract linear algebra and abstract algebra, so you'll understand some of these concepts from the scratch. So here, where EI belongs to the D-dimensional real number system, here D is the embedding dimension. For example, it can be 768, 1024, or 4096. So RD denotes a D-dimensional real vector space. Thus, every word eventually becomes a point in a high-dimensional mathematical space. So it's mathematics all the way. So the key takeaways from this idea: computers cannot understand language directly. Then every sentence must first become numbers. Token IDs are identifiers, not meanings. Embeddings provide meaningful numerical representations, and all modern large language models operate on vectors rather than words. Now we're going to talk about tokens, which are the building blocks of language models. So a token is the smallest unit of text that a large language model processes. So although humans usually think in terms of words, language models think in terms of tokens. So that's why it's all about tokens, right? So a token can represent an entire word. It can be part of a word. It can be a punctuation mark. It can be a number, a mathematical symbol, even a space in some tokenization schemes. So every sentence you type is first broken into tokens before any further processing occurs. Now the question is, why not use whole words then? Why not use whole words? Why break words down into smaller portions? Now, if every unique word were stored separately, the vocabulary would become enormous. For example, you have play, playing, played, player, playful, and replay. If you have to use these words, where these words share common parts, so instead of having to have them as separate words, so if you break it down, if you have play as a token, you can easily join re and play to get replay. You can easily join play and full to get playful. You can join play and er to get player, and so on. So this was share common parts. So instead of storing every possible word, language models often split words into smaller pieces called subword tokens. So this significantly reduces vocabulary size while allowing the model to understand new words it has never seen before. So for instance, if you're doing this separate words now, so you have one, two, three, four, five, six. And instead of having one, two, three, four, five, six, you can just have play, and then you now have all the endings added to it, which will also be useful in other contexts. So this simply reduces vocabulary size while allowing the model to understand new words it has never seen before. Example one, consider the sentence: ChatGPT understands context. Now, one tokenizer may produce chat in position one, GPT in position two, three understands, four context, and five the full stop. Another tokenizer may produce one chat GPT altogether, and then two understands altogether, three is context, and four is full stop. Now, different language models use different tokenization algorithms. So it depends on the kind of tokenizer you're using. Now, example two, consider the sentence: machine learning changes everything. Possible tokens are one machine, two learning, three changes, four everything, and five is full stop. Thus, n is equal to five here. So n equals five tokens are processed in this place. But if you have to use subword tokenization, consider the long word electroencephalographically. Instead of treating it as one enormous word, the tokenizer may split it into electro. So electro can work for electronics later. Encephalo can work in another context beyond this one. Graphic can work in another context, and Ali can work in another context. So, or you can have another similar decomposition. So this allows the model to understand unfamiliar words by combining known pieces. So with this now, you can have so many other words that can just borrow any of these subword tokens. And then we have token IDs. Now, each token is assigned a unique integer called a token ID. For example, chat can be 5218, GPT is 13672, understand is 8142, context can be 6120, and full stop is 101. So these numbers are not mathematical values actually. So they simply identify entries in the model's vocabulary. So they're more like entry numbers into a token dictionary, if you like. Then you then have mathematical representation. So suppose a sentence contains n tokens, the tokenizer produces T1, T2 up to Tn. Each token is assigned a unique integer I1, I2 up to In, where Ik belongs to 1 to up to V like that. And V is the vocabulary size. I sub k is the token ID corresponding to the token TK. So for many modern languages, then we see that the vocabulary size is greater than 50,000. So some models have vocabularies containing more than 100,000 tokens like that. So in that case, V is about 100,000. So now why does tokenization matter? The number of tokens directly affect processing speed, memory usage, API cost, maximum conversation length. For example, a sentence containing 100 words may produce 90 tokens, or 120 tokens, or even 150 tokens, depending on the tokenizer. This is why different models can report different token counts for the same text. Now, having a real world example, suppose you ask ChatGPT, suppose you ask ChatGPT, explain artificial intelligence using simple language. So internally, the processing pipeline begins as this. You have the sentence broken down into tokens from T1 to Tn with token IDs I1 to IN. At this stage, the model still has no notion of meaning. So meaning only emerges after these token IDs are converted into embeddings, which will be studied in the next section. So we have some key takeaways here. Tokens are the basic units processed by language models, and a token is not necessarily a complete word. Long words are often split into subword tokens, and every token receives a unique token ID. Tokenization is the first mathematical step in every ChatGPT conversation, and the sequence of token IDs is later transformed into embedding vectors that capture semantic meaning, and then we go for that. Talking about token relationships now, how ChatGPT learns language. Now, tokenization breaks a sentence into individual tokens, but tokens by themselves carry very little information. So the real power of a large language model comes from learning relationships between tokens. So rather than memorizing complete sentences, ChatGPT learns which tokens frequently appear together and how they influence one another in different contexts. So why relationships matter then? Consider the sentence, the cat chased the mouse. So humans immediately recognize the following relationships. Cat is the subject, chase is the action, and mouse is the object. So these relationships allow us to understand the meaning of the sentence. Similarly, ChatGPT learns statistical relationships between these tokens during training. Example one, you have a sentence, the cat chased the mouse. The token sequence may be the cat chased the mouse with this numbering. Then the model learns relationships such as cat chased, chase mouse, cat mouse. These relationships help the model predict missing or future tokens. And then in example two, suppose the sentence is the doctor examined the patient. Relationships include the following: doctor examined, examined patient, and doctor patient. Although the words differ from the previous example, the underlying sentence structure is similar. So the model gradually learns these structure patterns from billions of examples. So, and then we talk about context determining relationships. So context determines relationships. Consider the word bank in the sentence. She deposited money at the bank. The surrounding tokens deposited and money suggests that bank refers to a financial institution. Now consider the fisherman sat beside the bank. Here, the surrounding tokens, fisherman and beside, indicate that bank refers to the edge of a river. Thus, the relationship between tokens determines meaning. So, relationship between tokens determines the meaning, and all that. So, because those relationships are like contexts, predicting the next token. Then, one of the primary tasks of a language model is to predict the next token. Suppose the sentence, the Earth revolves around the dash. So, the model estimates probabilities for many possible tokens like Sun, Moon, Galaxy, and Earth. And then Sun 0.96, Moon 0.02, Galaxy 0.01, and Earth 0.01. Now, the Sun has the highest probability, and then it is selected. So the Sun revolves around the Sun. The Earth revolves around the Sun based on the probability you have here. And then we talk about conditional probability. Mathematically, the model estimates probability of a token at the next time step based on the tokens at previous time steps. So T1 to Tn are previous tokens, Tn plus 1 is the next token, and the probability denotes conditional probability. This equation is the foundation of autoregressive language modeling, and I mean it can be connected to the idea of Bayesian theorem. Bayesian theorem. So, and we have lookup relationships. Some relationships involve nearby tokens. Example, artificial intelligence changes education. So relationships can include artificial intelligence, intelligence changes education. These nearby relationships are often sufficient for understanding short phrases. So we are dealing with a short phrase. These simple connections can actually give you the context of what you're dealing with. Now, we can now have long range relationships. Some relationships span long distances. For instance, the professor who taught the graduate students during the summer semester received an international award because she developed a revolutionary algorithm. So the word she refers to professor, even though many words separate them. Understanding such long range relationships is one of the major strengths of transformer models. So we can then talk about a relationship graph. We can visualize token relationships as a graph. So you have professor, taught, student, develops algorithm. So each connection represents, so you can have professor taught, taught student, taught developed algorithm. Each connection represents a statistical dependency learned during training. And then you have the mathematical representation. Suppose a sentence contains T1, T2 up to Tn. The relationship between two tokens can be represented by a function R of Ti, comma Tj, which measures how strongly token Ti is related to token Tj. So later, the transformer computes these relationships using the attention mechanism, which assigns weights to pairs of tokens. So to get that relationship between T1 and T2, T1 and T3, T1 and T4, and then T2 and T3, and just goes on like that. So the transformer computes these relationships using the attention mechanism, which assigns weights to pairs of tokens. So we talked about attention in the last video. The attention weights between token I and J, token I and token J is denoted by Aij. So where larger values indicate stronger relationships. So this attention weights allow the model to focus on the most relevant parts of the context. So imagine ambiguous pronouns. Consider the sentence. The trophy did not fit into the suitcase because it was too large. Humans infer that it refers to the trophy easily. Now consider the trophy did not fit into the suitcase because it was too small. Was it the suitcase that was too small or the trophy? Now, this it here refers to the suitcase, although the sentence differ by only one word, large versus small. The relationships between the tokens change, leading to different interpretations. So these are ambiguous contexts. So why tokens relationships then matter? Learning token relationships enables ChatGPT to understand grammar, resolve ambiguous words, interpret pronouns, follow long conversations, generate coherent responses, answer questions based on context, a previous context. Without these relationships, the model would simply treat each token independently and will be unable to understand language. So the key takeaways here: language understanding depends on relationships between tokens rather than isolated words. Then ChatGPT learns statistical dependencies from enormous text data sets. And then the next token is predicted using conditional probabilities. Both nearby and long range relationships contribute to contextual understanding. These learned relationships are later quantified using the attention mechanism, which forms the mathematical core of transformer models. Now, let's talk about embeddings, turning words into mathematical meaning. So after tokenization, ChatGPT has a sequence of tokens, token IDs. However, token IDs alone contain no semantic information. So for example, you have cat with all these numbers, cat, dog, car with all these token IDs. Although cat and dog are semantically similar, their IDs have completely unrelated numerical values. Therefore, the model converts every token into a dense numerical vector called an embedding. Embeddings are one of the most important ideas in modern artificial intelligence. Now, the question is, what is an embedding? An embedding is a vector of real numbers that represent the meaning of a token. Instead of representing cat as 1542, the model represents it as something like ecat, which is 0.42 minus 1.15, 0.87, 0.31, and so on. This vector may contain hundreds or even thousands of numbers like that. So these numbers collectively capture semantic information about the word. So then you talk about the embedding space now. Every token is represented as a point inside a very high dimensional space called the embedding space. For example, dog might become 1.24, 0.83 minus 0.52, and so on and so forth, while puppy might become 1.18, 0.91 minus 0.48. You can see they are similar. Since these vectors are close together, the model recognizes that the two words have similar meanings, dog and puppy. Of course, puppy are baby dogs, so to speak. Meanwhile, if you talk about airplane, airplane may have an embedding far away from both dog and puppy. And then you talk about high dimensional vectors. In practice, embeddings are not two-dimensional or three-dimensional. They usually have dimensions such as 768, 1024, 1536, 2048, 4096. Now, suppose the embedding dimension is D768. Then each token is represented as E equals E1, E2 up to E768, where each component is a real number. And then for the mathematical definition, suppose the vocabulary contains V tokens. Each token is mapped into RD, the D-dimensional vector space, where V is vocabulary size and D is embedding dimension. Mathematically, a function a function f maps one to the vocabulary size to the embedding dimension. Then the function f maps each token ID to its corresponding embedding vector. So embedding matrix now. Instead of storing embeddings individually, the model stores them inside a large matrix. Suppose vocabulary size V is 50,000, embedding dimension is 768. Then the embedding matrix is going to be E, which belongs to the 50,000 by 768 vector matrix space. So each row corresponds to one token. So for example, this is one token, another token, until you get the 768 column we have 50,000 rows and 768 columns. If a token has ID 1452, the model simply retrieves row 1542 rather. If a token has ID 1542, the model simply retrieves row 1542 from the matrix. So, example one now. Suppose our vocabulary contains only four words: cat, dog, car, and apple. Suppose the embedding dimension is D equals 3. So the embedding matrix becomes, so for cat, so we get, so maybe you have to do about color, the structure and everything. So these are the dimensions there. So for cat, you have 1.2, 0.9, 0.4. For dog, you have 1.1, 1.0, 0.5. For car, because they are totally different from cat and dog, you now have like minus 2.4, 3.1, 1.8. And for apple, you have 0.3, minus 1.8, 2.5. Therefore, e-cat will be this first row you have here. E-dog will be the second row. Notice that these vectors are very similar because cat and dog are sort of similar. Now, why similar words have similar embeddings? Consider the words king, queen, prince, princess. These words often appear in similar contexts during training. So consequently, gradient descent adjusts their embedding so that they occupy nearby regions of the embedding space. Likewise, doctor, nurse, hospital, patient also tend to cluster together. This organization emerges automatically during training, depending on the embeddings, right? So we then have geometry of meaning. Imagine a simplified two-dimensional embedding space. You have lion, you have cat, you have dog, you have car, you have airplane. So nearby points represent similar meaning. So lion, cat, and dog are similar. Car, airplane are similar. So far apart points. So imagine lion to airplane, that's totally far. Maybe car is even a bit closer. Then we can talk about the shape and all that. Then, although real embedding spaces have hundreds of or thousands of dimensions, the same geometric intuition does apply. Then we have example two. Now suppose that x is 2, comma 1 represents dog, while y, which is 2, comma 2, represents cat. The Euclidean distance to be, the distance between them, that's a square root of 2 minus 2 squared plus 2 minus 1 squared, and you get 1 there. Now suppose z is 8, comma 9, so it represents cat. Then the distance between, so then you now have 8 minus 2, 9 minus 1. Now cat and dog. So you see the distance is now 10. Now you see, since 1 is less than 10, we can say dog is much closer to cat than to cat. So let's talk about embeddings learning automatically. Embeddings are not manually designed because I mean almost impossible because you have, especially when you have thousands of dimensions. So they are not done manually, they're done automatically by the machine. So initially every embedding consists of random numbers. During training, the model makes predictions, errors are computed, gradient descent adjusts the embedding vectors. Similar words gradually move closer together. Then, after billions of training examples, the embedding space acquires meaningful structure. So, imagine here now, you have Python example one now, creating an embedding layer. So, we use PyTorch here. So, you import torch, so import touch.nn as nn. Vocabulary size is 10,000. Embedding dimension is 1 to 8. So the embedding itself is now is nn. So that's touch.nn embedding. Vocabulary size with the embedding dimension. And by the time you put that together, you get 1,000 by 128. And that's exactly what this gives us here. Now this indicates that each of the 10,000 tokens has a 128 dimensional embedding. So looking up the embeddings now, if you check it up, so for tokens now, you have token 10, touch tensor 3, 8, 15. So the vectors embedding of the tokens now, you have the vector shape to be 3 by 128. All right. So each token has been converted into a 128 dimensional vector. So that's why if you do this now, token is touch.tensor15, vector is embedding token, and print vector is equal to embedding of token, and then print the vector, and you have this kind of array here. So the output is a tensor containing 128 floating point numbers representing the embedding of token 15. So that's it. This is the embedding of token 15 now. Now, why embeddings are powerful? Embeddings enable language models to measure semantic similarity, recognize synonyms, capture contextual relationships, generalize to unseen text, and perform mathematical operations on language. So without embeddings, modern language models such as ChatGPT would not be possible. So the key takeaways here, talking about token IDs, right? Embeddings, right? Token IDs contain no semantic meaning, but then embeddings convert tokens into dense numerical vectors. So similar words occupy nearby regions of embedding space. Embeddings are stored in a large embedding matrix. They are learned automatically during training using gradient descent. And embeddings, I mean, we've seen how gradient descent is used for in the learning process to adjust weights and biases so that so that loss can be minimized. So embeddings provide the mathematical foundation for contextual language understanding. Then we go to 31.6 where we talk about measuring semantic similarity, talking about cosine similarity now. So, I mean, we've done this, previously. So one words have been converted into embedding vectors. Once words, rather, have been converted into embedding vectors, ChatGPT must determine how similar two words or sentences are. This is accomplished using mathematical measures of similarity. So the most widely used measure in natural language processing is cosine similarity. Cosine similarity compares the direction of two vectors rather than their absolute lengths. So this makes it particularly suitable for comparing embeddings. So, why measure similarity then? Suppose the model encounters the words dog, puppy, wolf, car. Intuitively, dog is very similar to puppy, dog is somewhat similar to wolf, then dog is very different from car. So, you see levels of relationship now. Embeddings capture these relationships numerically, and cosine similarity provides a mathematical way of measuring them. So then we have the dot product because we have that used in cosine similarity. So before introducing cosine similarity, recall the dot product of two vectors. Suppose x is x1, x2 up to xd, and y is y1, y2 up to yd. The dot product is simply x dot y, which is x dot y, is equal to the summation of all the products corresponding products of x and y. So x I y I from x equals I to d. So the dot product measures how much two vectors point in the same direction. How much do they point in the same direction? So talking about vector magnitude now, because we also need that for cosine similarity. So vector magnitude, the length of magnitude of a vector, which is, for instance, magnitude of x is square root of x1 squared plus x2 squared plus xd squared, like that. Then similarly, you have the same for the norm of y, or what you call the gradient or the vector magnitude of y rather, and that is square root of y1 squared plus y2 squared up to yd squared. Now, these magnitudes are used to normalize the vectors before comparing them. So cosine similarity formula then becomes this cos theta x dot y, that's the dot product all over the product of the magnitudes. Hence, x and y are embedding vectors, and theta is the angle between them. So the interpretation is this. The cosine similarity lies between -1 and 1. So the interpretation is that if you get 1, it means the two vectors are in the same direction. 0.9 means they are extremely similar. 0.7, they are strongly related. 0.5, they are moderately related. 0, they are totally unrelated. And -1 means they are in perfectly opposite directions. In practice, embedding similarities are usually between 0 and 1, like that. Uh, so usually between 0 and 1. So an example, suppose x is 2, 3 and y is 4, 6. Compute the dot product. You have 2 times 4 plus 3 times 6. That's 8 plus 18, which is 26. In step 2, compute the magnitudes now. So for x now, x is square root of 2 squared plus 3 squared, which is root 13. For y, you have square root of 4 squared plus 6 squared, which is root 52. And in step 3 now, if you compute cosine similarity, that's 26 over root 13 over root 52. So, and you know root 52 is 2 root 13. So we obtain cos 30 to be 26 over 26, which is 1. So the vectors point exactly in the same direction. I mean, that's also easy to say because you can see y is simply 2 times x. So y is 4, 6, x is 2, 3. So y is 2 times x. So they are basically in the same direction. So in example 2 now, suppose we have 1, 0, 0, 1. The dot product is 1 times 0 plus 0 times 1, which is 0. And the magnitudes are 1 each. So cos theta is 0. So these vectors are orthogonal, indicating no directional similarity. They are at angle 90 degrees to themselves. They are perpendicular. So in example 3 now, if dog is 12, 1.20.8 and puppy is 1.10.9, the cosine similarity is approximately 0.997, indicating that the two embeddings are extremely similar. So now compare dog, which is 1.2, 0.8, and car, which is minus 1.2, 3.5. The cosine similarity might be 0.18, indicating very little semantic similarity. So this is pretty close to 1, and this is way far from it. Now, why cosine similarity instead of distance? Why do we use cosine similarity instead of distance? So consider 1, 2, and 2, 4. Although the second vector is twice as long, they point in exactly the same direction. So cosine similarity recognizes this and gives value of 1. But Euclidean distance, however, would incorrectly suggest that the vectors are far apart because you're going to have to do square root of 2 minus 1 squared plus 4 minus 2 squared. And you're going to get a big number. So this is going to be 1 squared plus 3 squared. And 1 squared plus 2 squared, that'll be 1 plus 4, 5. Whereas this has only told us one that they're in the same direction. So for semantic comparison, direction is generally more important than length. So direction over length. So semantic embeddings now, sentence embeddings. Cosine similarity is not limited to individual words. So entire sentences can also be represented by embeddings. For example, if you have some sentence A, artificial intelligence is transforming education, and sentence B says AI is changing the way people learn. So these two sentences may have cosine similarity of 0.94, indicating that they convey nearly the same meaning despite using different words. So for instance, if you are computing cosine similarity here, x is 2, 3, y is 4, 6. I mean, this is exactly what we did before. So if you do this now, you see that the result is 1, roughly 1, meaning that these two vectors are in the same direction because the cosine similarity is 1. So if you using scikit-learn for the same thing, you have 2, 3, 4, 6 now. So for scikit-learn, you have a function called cosine similarity directly. So you have cosine similarity of x and y. So you get 1, perfectly 1. That means they're in the two vectors are in the same direction. In example 3 now, you want to compare multiple embeddings. So using cosine similarity from scikit-learn metrics.pairwise. So embeddings array, so dog 1.2, 0.8, puppy 1.1, 0.9, cat minus 2.1, 3.5. So to get similarities now, so you have cosine similarity of the embeddings. So it tells you that so it means you have dog puppy car. So one here, so each of them, so this is the constant similarity between dog and dog. That's perfectly one, which is understandable. Then this is dog, so dog puppy car. So this is dog and puppy 0.9, and because they are close. Then dog and car 0.04, that's far away. And then you have next now you have puppy and dog, same 0.99. Puppy and puppy, of course, one. Puppy and car, so you have 0.11144 and so on. So I mean down here you then have car and dog 0.04, car and puppy. Yeah, car and puppy 0.144, car and car is 1 like this. So this the resulting similarity matrix shows how similar every embedding is to every other embedding like that. So this is a very useful thing. So you can put all the embeddings together and then have a matrix of that. So talking about the applications of cosine similarity now, cosine similarity is widely used in semantic search, recommendation systems, in ChatGPT, in document retrieval, in text clustering, in duplicate document detection, in question answering, in information retrieval, in machine translation, and plagiarism detection. So far, the key takeaways from that whole idea of semantic similarity, we see that cosine similarity measures the angle between two embedding vectors, and it is computed using the dot product and vector magnitude. So yeah, we need dot product and vector magnitude to get cosine similarity. Then it is computed using the dot product and vector magnitudes. Then values close to 1 indicates highly similar meanings, and values close to 0 indicate unrelated meanings. Cosine similarity is one of the most important mathematical tools in modern natural language processing and large language models. So ChatGPT relies heavily on cosine similarity to compare embeddings. So we have all of that. So in the next section, we'll be looking at context windows, how ChatGPT remembers conversations like that. So context windows and how ChatGPT remembers conversations. Because one of the most remarkable features of ChatGPT is its ability to answer questions while taking earlier parts of a conversation into account. So it doesn't forget earlier parts of the conversation while as it progresses with the conversation. So this ability comes from something called the context window. So that's why this section is about context window. The context window defines how much information the model can consider at one time. So rather than remembering everything forever, ChatGPT processes a fixed number of tokens at once. So everything inside the window contributes to generating the next response. So now what is a context window? It is the maximum number of tokens that a language model rather, can process simultaneously. So suppose the context window has size n. Sometimes if you prompt ChatGPT, right, it tells you something like all your responses cannot come out at once. So it gives it to you in batches. So that's an idea of so each batch it gives you is like a context window. So then the model processes tokens one, two, tokens one, two, up to tokens n, where each TI is one token. So when predicting the next token, the model uses information from the previous tokens. And talking about mathematical representation, suppose the context consists of n tokens. The model predicts the next token using probability of Tn plus 1 given T1, T2 up to Tn. Notice that every previous token inside the context window can potentially influence the prediction. This is one of the major innovations of transformer models. So imagine this example one. Suppose you type, my favorite color is blue. And later you ask, what is my favorite color? Because the earlier sentence is still inside the context window, ChatGPT correctly answers blue. So the model does not remember in the human sense. Instead, the earlier tokens remain available for computation. So example two, suppose the conversation is user says, I have two dogs named Max and Bella. And several messages later, user says, which dog did I mention first? Since Max appears earlier in the context window, the model can answer correctly, though it doesn't understand Max and Bella, but it understands the whole, tokenization, embedding, and everything. And then it can correctly tell you it's Bella. You mentioned first. And now in example three, consider a mathematics lesson. Earlier in the lesson, you define f of x equals x squared plus 3x plus 2. So later you ask, differentiate the function. The model recognizes that the function refers to f of x equals x squared plus 3x plus 2, provided that the definition still lies inside the same context window. So, and then talking about sliding context window now, imagine the model has a context window containing only 10 tokens. Initially, you have T1, T2, T3, T4, T5, up to T10. After one additional token, you have T11. So you then have T2 to T11. So that has pushed out T1. So that's the sliding has started like that. So if the context window can only take 10 tokens, so one additional token will push out T1. So after if you add another one, it will push out T2. So if you add T11, T1 is out. If you add T12, T1 and T2 will be out. So you just have T3 to 312. I mean T12. So the oldest tokens gradually leave the window while new tokens enter. For this reason, the context window is sometimes described as a sliding window. So as you keep adding new things, other the earlier tokens will go. So why large context windows then matter? Larger context windows allow models to read longer documents, analyze research papers, understand books, follow lengthy conversations, write large computer programs, maintain consistency across long responses. Without a sufficiently large context window, the model would forget easily parts of the conversation. So imagine this example. Suppose a language model has a context window of n equals 8 tokens. The current sequence is artificial intelligence is changing modern education rapidly today. That's 8 tokens right there. The next prediction is computed using all 8 previous tokens after generating the word. So worldwide. The next context can then becomes intelligence is changing modern education rapidly today worldwide. So the first token, which is artificial, has now left the context window because there's only space for 8. So once you add worldwide, you knock off artificial. So once you add this worldwide now, artificial will be gone because it can only take 8 tokens, right? So artificial now has now left the context window. Now let's talk about context length and computational cost. Now suppose the context window contains n tokens. The attention mechanism compares every token with every other token. So the number of pairwise comparisons is approximately n squared. For example, if n is equal to 100, then 100 squared is 10,000. Comparisons are required. So if n is equal to 1,000, then 1,000 raised power 2, which is 1 million comparisons, will be required. Thus, doubling the context length more than doubles the computational workload. So this quadratic growth is one reason why efficient attention algorithms are an active area of AI research. So research continues on efficient uh, attention algorithms. Imagine this Python example, a simple simulation of a sliding context window. From collections, import the queue. So window size. So if you have a window size of 5 and then the context the queue, maximum length is the window size. So you can only have 5 tokens in your window this time around. So see the tokens. Artificial intelligence is changing education rapidly today. So for each token in these tokens now, you get the context and append the new token. So if you run this now, you then see that you have um, first is artificial, next you have artificial intelligence, next you have artificial intelligence is changing, next you have education, So now now because there's only space for five. So here this is one, this is one, two, this is one, two, three, this is one, two, three, four, this is one, two, three, four, five. Now see what happens. You still have everything from the beginning. Artificial intelligence is changing education. Now after education, once you add rapidly to push out artificial, so you then have intelligence is changing education rapidly. And by the time you add today, intelligence will be stricken off. So you have it's changing education rapidly today because the context window is can only take five tokens. Now notice how the oldest token disappears once the maximum window size is reached. So once the maximum window size is reached, any additional word will push out earlier tokens, basically. So look at example two, Python example two, computing the number of token comparisons. So here now, you define a function called attention cost n, and you return n squared. So if you have size is 128, if you double 128, no, is it double now? If you double 128, that's 256, right? So here it's like 512, that's quadruple it, and then double it, and then double that. So for n in size is now, if you compare now, so the number of comparison, if the context window is 128, pairwise comparisons will be 128 squared, which is 16,384. If it is 512, you get 262,144. If it is 1,024, you have 1,000,000, it's 48,576. If it is 2,048, you have 4,194,304. This illustrates why increasing the context window significantly increases computational requirements. So doubling the context window, you know, uh, raises. Okay, let's even try. Let's even check a quick code here. Let's check. So from 1 to 8, okay, see, print, if you print 512 over 128. So let's say you're printing that, and then you also want, so you now want to print, okay, let's say you print this. You want to print 262 262,144 divided by 16,384. So if you print this now, so imagine you only quadruple this, whereas the pairwise comparisons have been raised to has been 16 times, six. So if you only 4x this, and then the pairwise comparison is 16x, right? So the ratio with which you multiply it will be squared automatically. So this illustrates why increasing the context window significantly increases computational requirements. Then you have real-world applications. Large context windows make it possible to summarize lengthy reports, analyze legal documents, review scientific papers, debug large software projects, maintain coherent conversations over many exchanges, generate consistent long-form articles and books. So, talking about the limitations of context windows now, so every large context window, even very large context windows are finite, right? So it gets to a point it's saturated, and then consequently, very long conversations may eventually exceed the available context, and earlier information may no longer be available. So important details may need to be repeated or summarized. So memory outside the context window requires additional mechanisms beyond the basic transformer architecture. So for key takeaways now, a context window is the maximum number of tokens a model. So the maximum number of tokens a model processes simultaneously. So every prediction depends on the tokens currently inside the context window. Then the context window slides forward as new tokens are generated. So larger context windows improve long document understanding and conversational continuity. And then the computational cost of standard self-attention grows exponentially as O n squared. So making efficient attention mechanisms an important research area in modern AI. So that takes us to positional encoding. So that's teaching ChatGPT the order of words. So far, we have learned that ChatGPT converts words into embedding vectors. However, embeddings alone are not enough. Why? Because embeddings do not contain information about the order of words. So consider the following two sentences: dog bites man and man bites dog. So both sentences contain exactly the same words. If we simply added their embeddings together, the resulting vectors would be identical because it's basically the same words. Yet the meanings are completely different. Therefore, ChatGPT must also know where each token appears in the sentence. So this is the purpose of positional encoding. So the position is critical. So why word order matters, right? Language depends heavily on order. So consider these examples. Example one, the teacher praised the student. Example two, the student praised the teacher. The words are identical, but the meanings are reversed. Similarly, example three, I only borrowed your book. Example four, only I borrowed your book. A small change in position changes the emphasis and meaning. So here, only I and I only mean different things. I only borrowed your book. Only I borrowed your book. So therefore, the model must distinguish between T1, T2, T3, and T3, T2, T1 because of the position thing. So that's the idea of positional encoding. So the problem with embeddings alone, so if you have just embeddings, right? Suppose dog has embedding E1, bytes has embedding E2, and man has embedding E3 without positional information. The model simply receives E1, E2, E3. If the order changes, the embeddings remain exactly the same vectors. So the model would have no way of distinguishing the two sentences. So then comes positional encoding. So to solve this problem, each token receives an additional vector representing its position. So instead of using only E1, the transformer computes Z1, Zi equals EI plus PI, where EI is the embedding vector, PI is the positional encoding, and Zi is the final input representation. Thus, every token carries both semantic information and positional information. So meaning is not enough, position also matters. Now, suppose dog bites man contains three tokens, dog bites man, E1, E2, E3, and positional vectors P1, P2, P3. The transformer receives E1 plus P1, E2 plus P2, E3 plus P3. If you reverse the structure, the positional vectors also change, allowing the model to distinguish the two meanings. So we then have sinusoidal positional encoding. I think we saw that in the last video also. So the original transformer paper introduced a clever mathematical encoding based on sine and cosine functions. This is by Ashish Vashwani et al. So for position, you have POS, and embedding dimension, you have I. So the positional encoding PE plus 2I then is sine of the position all over 10,000 raised per 2I over D. And so you have PI for position for odd numbers now. So 2I plus 2I plus 1 equals cos position over 10,000 raised by 2I over D, where POS is the token position, D is the embedding dimension, and different dimensions oscillate at different frequencies, allowing every position to have a unique representation. Now, why do we use sine and cosine? Sine and cosine functions have several useful mathematical properties. For instance, they produce smooth continuous values and they naturally encode relative distances, allowing the model to generalize to longer sequences, preserve information about neighboring positions. For example, adjacent positions produce very similar vectors. So while distant positions become increasingly different, suppose D is equal to 4 and position is equal to 2. For the first dimension, PE is 2, 0. If you follow the PE formula, position 2i. So you have position. Here, I is 0. So sine 2 will be 0.909893. For the second position, PE is 2, 1. So you have cos 2, which is minus 0.4161. These numerical values become part of the positional vector added to the embedding, like that. So, and in example 2 now, suppose the sentence artificial intelligence changes education is what you have. So the positions are 1, 2, 3, and 4. Artificial intelligence uses education. Although artificial and education may have meaningful embeddings, their positional encodings distinguish whether they appear at the beginning or end of the sentence. So we then talk about learned positional embeddings here. So modern language models often replace sinusoidal encodings with learnable positional embeddings. Instead of computing PI using trigonometric functions, the model learns P1, P2 up to Pn during training, and these position vectors are updated through gradient descent, just like ordinary embeddings. This often improves performance for large-scale language models, and that takes us to Python example one, still talking about positions. So generating sinusoidal positional encodings, for instance. So import numpy as NP. So you define positional encoding with position and the model. So positional encoding, encoding, yeah, or embedding, you have NP zeros, you have the position, you have the model itself, and for position in the range of the position you have. So for I in range 0 to D model 2, so you have the angle, you have the positional encoding and all that. By the time you're done doing all of that, you have a positional encoding that is 5 by 8. So you have five, is it 5 rows now? 1, 2, 3, 4. Okay, not quite this. So this is 1, 2, 3, 4, 5. Yeah, this is it. 1, 2, 3, 4, 5, 6, 7, 8 columns. And then the rows. This is one row, 2, 3, 4, 5. So this is 5 by 8. So when we print the PE, you now get these values like this. So talking about the positions, so now you are generating this we are generating the sinusoidal positional encodings. Now this generates positional encodings for 5 token positions using an embedding dimension of 8. So you have a 5 by 8 positional encoding right there. So for example 2 now, we want to visualize positional encodings. So instead of just having it in numbers, so it's good to see it visually. So in that case, we need matplotlib. So here we are basically plotting you are showing the image, the positional encoding. You're using aspect auto and CMap viridis. Of course, we can always change the CMap. CMap is the color map. So see what you have here now. So you can see here things are a bit nuanced, but here it's just vertical lines all the way. Now, of course, just like I said, we can change viridis to say rainbow. Rainbow. So we have this. So you have the colors changing. So I mean, you can just play with that. So here you have sinusoidal positional encoding. Now so you see the token position and see the embedding dimension right here. And this is a representation of what exactly you have up here. So instead of having numbers, you then have this beautiful representation. So the heat map illustrates how different positions produce distinct encoding patterns. So see position 0. So position 0 at embedding 0 is this light green or so. And then position 0 at embedding dimension 1, it's red. And then when you get here, it's things are widening out. And then here, so it doesn't matter what the embedding is or what the position is, you just have the same colors all through. So, but in the first from zero, embedding dimension 0, 1, 2, you have nuances, but the rest they are just like same. Now, then we talk about Python example 3. So if you want to combine embeddings with positional encodings, so you have embeddings, NP random, so combine 5 8 input representation, you have the embedding plus positional encoding, and that ends up being 5 8, like we saw before. So each token now contains both semantic and positional information. So why positional encoding is then essential? Without positional encoding, the transformer would treat dog bites man and man bites dog as the same thing, whereas they mean different things, and that can be misleading, right? So, these are identical collections of words, but positional encoding enables the model to understand sentence structure, distinguish subjects from objects, preserve grammatical meaning, process long sequences accurately. It is one of the key innovations that made transformer-based language models successful. So, the key takeaways we have from here, from the idea of positional encoding, is that embeddings alone do not encode word order. Positional encoding tells the model where each token appears, and the original transformer used sinusoidal functions based on sine and cosine, and many modern models use learnable positional embeddings instead. So the final input to the transformer is zi equals ei plus pi. So positional encoding enables ChatGPT to distinguish sentences with identical words but different meanings, so that you can then know that man bites dog is different from dog bites man. So, so talking about attention, I mean, the last video I think was totally dedicated to attention, to the idea of transformers, which came with attention. So, the secret behind ChatGPT's understanding of context now, one of the greatest breakthroughs in artificial intelligence is the attention mechanism. So, attention is the mathematical process that allows ChatGPT to determine which previous tokens are most relevant when processing and when processing the current token. So, instead of treating every previous word as equally important, the model learns to focus its attention on the most informative parts of the context. So this ability enables ChatGPT to understand long sentences, resolve ambiguities, answer questions, and generate coherent responses. Now, why is attention needed? Consider the sentence. The trophy did not fit into the suitcase because it was too large. And what does it refer to? Humans immediately infer that it refers to the trophy. Now consider the trophy did not fit into the suitcase because it was too small. Now it refers to the suitcase. So although the two sentences differ by only one word, large versus small, the relationship between the words, attention enables the model to discover these relationships automatically. Now imagine another example. So consider Emmanuel teaches artificial intelligence because he enjoys mathematics. I guess that is me right there. So the word he refers to Emmanuel. So the model identifies this relationship by assigning a strong attention weight. It's a strong attention weight between these two tokens. So the basic idea, suppose a sentence contains n tokens, T1, T2 up to Tn. When processing token Ti, the model examines every token in the sentence Instead of giving every token equal importance, it computes a numerical with aij representing how much attention token ti should pay to token tj. So large values indicate strong relationships and small values indicate weak relationships. So that way we can then visualize the attention. Suppose the sentence is the cat chased the mouse. So a simple attention diagram might look like this. The cat, so the cat chased, a mouse chased. So, and then that leads to our prediction. Here, the word chase pays the greatest attention to cat. All right. So, and then mouse, because they determine who performs the action and who receives the action. So the chasing was done by the cat and the chasing was done on the mouse. So, and then we have the query key value, which comes with the whole idea of attention. So every token embedding is transformed into three vectors. So you have query key value. These are usually abbreviated as QKV. Each token therefore produces QKV. These vectors are learned during training. And why three vectors? Think of attention as searching a library. So you query asks, what information am I looking for? And the key describes what each token contains, and value stores the actual information to retrieve. So the model compares every query with every key. So these corresponding values are then combined according to the resulting attention scores. So then talking about computing attention scores, you then have, suppose you have Q is a query vector and K is a key vector. Their similarity is measured using the dot product Q dot K. A larger dot product indicates greater relevance, like that. And then you have a scaled dot product attention. So the transformer computes attention using attention as a function of Q, K, and V by computing the softmax of the dot product between Q and K with a matrix of that QK transpose, and it is normalized or scaled using by the dimension. So you have by the square root of dk multiplied by the value. So where Q is the query matrix, K is the key matrix, V is the value matrix, and dk is the key dimension. So this equation is the mathematical heart of every transformer model. So understanding the formula now, I mean, I've made attempt a lot to interpret the formula. So the computation proceeds in several steps. First of all, you compute QK transpose, which is the dot product between the query and the vector, the query and the key values. Now, I mean, the query and the key matrices. So this measures the similarity between every query and every key. Then step two, you scale the vector, the scores now. So you have QK transpose divided by the square root of dk. So scaling prevents very large dot products from causing unstable gradients during training. And in step three, you apply the softmax function. So softmax of xi is simply the exponent of xi all over the summation of all the possible exponents of x. So softmax converts arbitrary scores into probability that sum to 1. So that way you have a probability distribution. So that way you can then multiply by v. So the weighted combination of value vectors become the contextual representation used by the next layer. So in that case now, you then have the example. Suppose a token has attention scores 210. Applying the softmax function gives approximately, so that means e raised power 2, e raised power 1, e raised power 0, and then so for 2 all over e raised power 2 over e raised power 2 plus e raised power 1 plus e raised power 0 will give you 0.67. E raised power 1 all over e raised power 2 plus e raised power 1 all over plus e raised power 0 will give you 0.24, and e raised power 0, which is 1. So you have 1 all divided by e raised power 2 plus e raised power 1 plus e raised power 0, you get 0.09. This means the first token contributes about 67%, and the second contributes 24%, while the third contributes only 9%. So the model therefore focuses primarily on the first token because the first token carries more weight. So it requires more attention. And that is where the idea of attention comes from. So talking about self-attention now, the transformer uses self-attention. This means every token attends to every other token in the same sentence, including itself. So suppose the sentence is artificial intelligence changes education. So it means for your predictions, so you're going to have a relationship between every pair of words. So artificial intelligence, artificial changes, artificial education. Then you have intelligence changes, intelligence education. Then you have changes education. So the attention relationships may look like artificial, so intelligence, artificial education, then artificial changes, intelligence changes, and all of that. So each word exchanges information with the others, allowing every token to build a richer contextual representation. So you want to see what is the connection in terms of attention between every pair of words you can ever have, and then we can have an attention matrix like this. So for a sentence containing n tokens, so for a sentence containing n tokens like this. So the attention scores form an n by n matrix, right? Because every word, in fact, every word is compared with itself and other words. So you have, that's why you have A11. So between one and one, then ANN between N and between every other one in between. That's why you have an N by N the N by N matrix that the attention matrix, attention scores forms. So the entry Aij represents how much token I attend to token J. So each row of the matrix sums to 1 after the softmax operation. So every row sums to 1. Then we talk about multi-head attention, like we said in the other video, the previous video before this. So instead of computing attention once, transformers compute it multiple times in parallel. Suppose there are H attention heads. Each head learns different types of relationships. For example, one head may learn the grammar, another pronoun resolution, another long-range dependencies, another semantic similarity. The outputs from all heads are then combined. This enables the model to capture many kinds of linguistic information simultaneously. So if you try this, imagine you have attention scores 210. Okay, I mean, just what we did over there. And then the exponent of the scores now. So you get the exponent of each score, and then you do the softmax, which is the exponent of each score over their sum. And this is just what we did here. And to get 0.67, 0.24, and 0.09. So for example, 2 now, to compute dot products, now imagine you have your query is 1, 2, and the key is 2, 1, 1, 3. So if you do Q K transpose, this is so like that, you then have the scores will be 4, 7. So the second key now, so you see the first key is 4, the second key is 7. So the second key is more relevant because it produces the larger dot product. So it requires more attention. So going to example 3, talking about the scaled dot product attention. So imagine you have Q is 3 for, K is 3 for, V is 3 for also. So you have scores now, Q multiplied by K transpose, and then you compute the scores, you get the weights and all of that. You finally have the output shape. You have a 3 by 4. So the outputs consist of contextualized embeddings, one for each token. So here you have 3 by 4. Now the question is, why attention changed AI? Why did attention change AI? In fact, the last video was all about why transformers replaced every other AI model, and that is because of attention. So why attention changed AI? Before transformers, recurrent neural networks processed text sequentially, making it difficult to capture long-range relationships. So attention allows every token to interact directly with every other token, regardless of their distance in the sentence, in the sequence. So this innovation dramatically improved machine translation, question answering, document summarization, code generation, conversation AI, and many other AI applications. So it is widely regarded as one of the most influential ideas in modern deep learning. So that's attention, right? And the key takeaways we have here is that attention allows ChatGPT to focus on the most relevant tokens in the context. So each token generates a query key and value vector. Then the core attention equation is attention of QKV is softmax, QK transpose over square root of DQ multiplied by V. So self-attention enables every token to interact with every other token. The multi-head attention captures different types of linguistic relationships simultaneously. So grammar, context, all these things, pronouns, and all that. So attention is the mathematical mechanism that gives transformer models their remarkable contextual understanding. Now the question is how ChatGPT understands an entire conversation that is putting everything together. We have now studied the major building blocks of ChatGPT, like tokenization. When you put your prompt, you have your prompt is tokenized, and so the tokens are embedded, and then token relationships are established, and then you have context windows, and you have positional encoding, and you have attention to see which of the tokens requires the highest attention. So the question now becomes, how do all these components work together to produce an intelligent response? So the answer lies in the complete transformer pipeline. So every time you send a message to ChatGPT, the model performs millions or even billions of mathematical operations in just a fraction of a second, because you have that simultaneous thing going on. So you then have the complete pipeline. Suppose the user types explain machine learning. So the processing pipeline is text. So you put your text, which is explain machine learning. So that is now broken down into tokens. Maybe one word can be a token, or even some words can be broken down further. And then each token is given an ID, and then they are embedded with using vectors, and then positional encoding is added to it. So both the embedding and positional encoding together, then we now see which one requires more attention, and then we have a feed forward network, and then we have a probability distribution, and then we choose the next token based on which one highest probability. So each stage transforms the information into a richer mathematical representation. And then, so let's break it down. So talking about input text now, the conversation begins with ordinary human language. Explain machine learning in simple terms. At this stage, the input is simply text, so which is explain machine learning in simple terms. So the next stage is tokenization. So explain machine learning in simple terms. So let's say each word is a token and the full stop is also a token. So each token receives a unique identifier. And then once each text is given a unique identifier, you then have the embedding lookup. So each token ID is converted into an embedding vector. Mathematically, IK is assigned EK, where IK is the token ID and EK is its embedding vector. So instead of processing words, the transformer now processes vectors. In step 4, you add positional encoding. So each embedding receives positional information, and the input to the transformer becomes ZK equals EK plus PK, where EK is the embedding and PK is the positional encoding. Now, the model knows both what the token means and where it does appear, the position. And then we go on to talk about self-attention. Now, the transformer computes queries, keys, and values for every token. Then attention weights determine which earlier words are important. For example, when processing it, the model may strongly attend to machine learning instead of explain. So this allows context-dependent interpretation in that case. And then we have the feed-forward neural network. So the contextual representations produced by attention are passed through a neural network. So each transformer layer contains a feed-forward network that learns increasingly complex language patterns. So a simplified representation is then this H equals W2. This is like a weight now. And then you have the weights multiplied by inputs with the bias thrown into a function, activation function, and then so that forms so this now forms um a new input, right? Multiplied by a new weight and a new and then added with a new bias added. So W1 and W2 are weight matrices, B1 and B2 are bias vectors, sigma is an activation function, X is the attention output, and this stage performs nonlinear feature extraction. And then that takes us to the multiple transformer layers. The previous steps are repeated many times. So suppose the model has L transformer layers, then you have X naught. So you have the first set of inputs, it goes through the process, activated, another weight is multiplied, and you have bias. So it takes you to 1, and then you go all the way to L. So each layer produces rich contextual representations. So layers often learn grammar, punctuation, and sentence structure, and early layers rather often learn grammar, punctuation, sentence structure, while deeper layers learn reasoning, semantics, long-range relationships, and abstract concepts. And then we talk about predicting the next token. After processing all transformer layers, right, the model computes a probability for every token in its vocabulary. So suppose the vocabulary contains V tokens, the output is then PT, probability of T1, probability of T2, all the way down to probability of TV. So this probability satisfies that summing it all together is 1. So the most probable token is usually selected or sampled depending on the coding settings. So imagine this example. Suppose the model predicts it uses, refers, means, computes with all these probabilities now. So is most common. So the largest probability is 0.42. So the model generates is as the next token. So the entire process repeats again for the following token, and it keeps going like that. So we have the autoregressive generation. ChatGPT generates text one token at a time. So suppose the desired sentence is artificial intelligence is transforming education. The model generates artificial. The next step, artificial intelligence. Next step, artificial intelligence is. Next step, artificial intelligence is transforming. Next step, artificial intelligence is transforming education. So it goes sequentially like that. So each newly generated token becomes part of the context for predicting the next one. So for a mathematical view on that now, suppose the generated sequence is T1, T2 up to Tn. The probability of the entire sequence is then the multiplication of all the probability of Ti given T1 up to Ti minus 1. So this equation is known as the chain rule of probability. So it is the mathematical foundation of autoregressive language models such as GPT. So imagine here, so you have text, artificial intelligence is amazing. So you break it down into tokens. So you split the text. So when you split, you have artificial intelligence is amazing. So it gives you the tokens. So split into words now. So real tokenizers are more sophisticated. So this is more like a tokenizer, now a simple tokenizer, which is just split of text. But so real tokenizers are more sophisticated than Python's split here. But that's just an example of what tokenizers can do. So a simple probability distribution. Therefore, is uses means and refers. So you refer all of that. So you want to see what is selected. So most like the one with the highest probability is most likely selected, and that is why is selected here. And then we go to Python example 3. So you want to generate tokens sequentially. So you have artificial intelligence is transforming education. These are generated tokens now. So for token and generated tokens, so you attend it. So the line 5 shows a this is an initializer. So this will take the words one after the other. So if you run this now, so later you join the sentences up. So you have artificial intelligence is transforming, artificial intelligence is transforming education. Then you have the complete flow diagram. So user input, that's your prompt. Then you have a tokenization going on. Then you have token IDs, you have embeddings, you have positional encoding, you have self-attention, you have feed-forward network, you have transformer layers, you have probability distribution, you have the next token, and you repeat until response is complete. So why does this pipeline work? So the architecture enables ChatGPT to understand context, recognize semantic relationships, capture language dependencies, generate coherent responses, answer questions, translate languages, write computer code, summarize documents, perform reasoning tasks, and engage in natural conversations. So the remarkable conversational ability of ChatGPT is not due to memorizing answers, but to repeatedly applying the mathematical pipeline to predict one token at a time. So we have key takeaways here. So ChatGPT converts text into tokens, embeddings, and contextual representations before generating responses. The positional encoding preserves word order. Self-attention allows every token to interact with every other token. Then feed-forward networks refine contextual information. Transformation, transformer layers progressively build richer representations. Then the final output is a probability distribution over the entire vocabulary. Then GPT generates text autoregressively by predicting one token at a time using probability of T1 given T1 up to T1 Ti minus 1. So this complete mathematical pipeline explains how ChatGPT understands context and produces coherent human-like responses. So talking about examples, under context, understanding context step by step now. In this section, we apply everything we have learned to see exactly how ChatGPT understands context in real conversations. So each example demonstrates how tokenization, embeddings, positional encoding, attention, and probability prediction work together. So resolving word meaning now. Consider the sentence, I deposited my salary at the bank. So the sentence is split into tokens 1 to 8. So each word and the full stop taking a position from 1 to 8, and you have the embeddings. Each token is converted into an embedding vector E1 to E8. These vectors represent semantic meaning rather than raw text. Then positional encoding. So each embedding receives positional information. So for example, Z7 is E7 plus P7, where E7 is embedding for bank. As you can see, bank is 7, and then the position is also 7. So attention so for attention, the token bank attends strongly to deposited and salary rather than I and at, because these nearby words provide the most useful context. So the attention weights might look like this: deposited 0.43, salary 0.37, then all the rest. So this model therefore concludes that bank is a financial institution in this case because of the context. Then resolving pronouns. Now Sarah gave Emily a book because she had finished reading it. Question: Who had finished reading the book? Is it Sarah or Emily? So of course, as humans, we know that should be Sarah, right? Then the model analyzes the relationships between Sarah, Emily, and she and it. Then attention weights help determine the most likely interpretation. So possible attention scores. So for previous token, Sarah is 0.62, Emily 0.18, book 0.20. So the model therefore predicts she here to be Sarah because Sarah is the most likely person who finished reading the book before giving it away. Now we have a mathematical context. Suppose the conversation suppose the conversation is this. The user says, let f of x be x squared plus 3x plus 1. A few messages later, the user then says, differentiate the function. The model connects the function with f of x equals x squared plus 3x plus 1, and the derivative becomes f prime of x, which is 2x plus 3, which is the correct way to differentiate. So the earlier mathematical expression remains inside the context window and is therefore available for reasoning. So if it does not, sometimes something you had done before, if you ask ChatGPT to refer to it, it tells you, okay, that you should supply it again. So that means that idea is probably no longer in the context window. So then, for example, for now, you have a long range context. So consider Emmanuel teaches artificial intelligence at the university because he enjoys helping students understand mathematics. So question, who enjoys helping students? The attention mechanism assigns strong weights to Emmanuel, rather than university or artificial intelligence. Thus, E is Emmanuel. So even though many words separate them, attention captures the long-range dependency. And in example 5, predicting the next token. Suppose the input is machine learning is a branch of blah blah. So the model computes probabilities over the vocabulary, artificial 0.81, mathematics 0.07, biology 0.04, physics 0.03, and all that. So the highest probability is artificial, that is 0.81. So the next generated token becomes artificial, and then the sentence now becomes mathematical learning is a branch of artificial, which is not complete, by the way. And then the process immediately repeats to predict the following token. So see the entire pipeline. Suppose the input is explain neural networks. So the complete pipeline is you have the input text, which is explain neural networks. Then you have tokenization, you have token IDs, you have embeddings, you have positional encoding, you have self-attention, you have transformer layers, you have probability distribution, and you generate the next token, and then you repeat. So every generated token is added back into the context before predicting the next one, and then it goes on like that. So talking about semantic similarity, suppose two sentence embeddings are X and Y like this. So the cosine similarity will be 0.996. That's just cosine similarity. That's take the dot product 1.8 times 1.9 plus 0.6 times 0.5 plus 2.1 times 2.0 all over the modular, the square root of this squared plus this squared plus this squared. Same for Y, and you add together and you get 0.996, which indicates that the two sentences have almost the identical meanings. Now, if you compare X and Z here, so the cosine is 0.14. This indicates that the meanings are largely unrelated. So you can even see from the values alone that they are not as close as these ones up here. Then we can talk about context window limitation. Suppose the model has a context window n equals 6 tokens. And then in current context, you have artificial intelligence transforms modern education rapidly. After generating today, the window becomes intelligence. So because this is pushed out and because this is saturated with 6, so intelligence transforms modern education rapidly today. So the token artificial has now left the window, the context window, and can no longer directly influence future predictions because it's done in the context window. So like the ones we said before, the two sentences with the with these values now, with these embeddings, we have 0.9981, which we saw before, and then for this probability, artificial math, predicting the most probable token now. So because artificial has 0.81, so it's easy to predict artificial in that case. Then for three now, simple sliding context window. So artificial intelligence transforms modern education rapidly today. And our window, the maximum length is 6. So here we have artificial. Maximum length is 6, so no problem. This is 1, 2, 3, 4. This is 5 here. And then this is 6. Once we have 6, any new word you add will push out. So you see artificial is here. So once you add a new word, after we have maximum of 6 now, to push out the first word, and then you have this. So if looking at the summary of the examples now, these examples illustrate that ChatGPT does not memorize answers. Instead, it repeatedly applies the same mathematical pipeline, convert text into tokens, convert tokens into embeddings, add positional information, compute attention scores, build contextual representations, predict the most probable next token, repeat until the response is complete, and this iterative prediction process enables ChatGPT to understand context, resolve ambiguity, maintain coherent conversations, and generate fluent, context-aware responses. And then we have the key takeaways there. Context is built from interactions among token embeddings. Attention determines which previous tokens are most relevant. Embeddings capture semantic meaning. Positional encoding preserves word order. Every generated token becomes part of the context for the next prediction. The same mathematical pipeline operates for every prompt, regardless of whether the task is conversation, coding translation, summarization, or even mathematical reasoning. So we see some real world applications of context understanding in ChatGPT. So understanding context is what transforms ChatGPT from a simple text generator into a powerful artificial intelligence system capable of solving real world problems. Nearly every modern application of large language models relies on the mathematical concepts we have studied: tokens, embeddings, positional encoding, attention, context windows, and probability prediction. Let us explore where these ideas are used in practice. So first of all, we have conversational AI. This is the most obvious application. When you ask ChatGPT a series of questions, it uses the context window to understand the conversation. Example, my favorite programming language is Python. Later, can you recommend a good book? So it knows you are referring to Python. So ChatGPT understands that the book should be about Python, so not about an unrelated topic. So without context, this conversation would be impossible. So we see that the application of context understanding in conversational AI, in machine translation now. Context is essential for translating languages correctly. So consider the English sentence. He sat by the bank. Without context, the word bank is ambiguous. However, he sat by the bank of the river clearly refers to the river bank. So modern translation systems use contextual embeddings to choose the correct translation. Then we have search engines now. Traditional search engines relied mainly on keyword matching. So modern AI search engines will instead compare embedding. So suppose a user searches best beginner AI books. A document containing introduction to artificial intelligence may be retrieved even though it does not contain the exact phrase beginner AI books. This is called semantic search. Now, instead of matching words, this search engine matches meanings. Then you have recommendation systems. Streaming platforms and online stores recommend content by comparing embeddings. For example, if someone watches linear algebra, machine learning, and neural networks, the system recommends the semantic similarity among these topics. It then can recommend deep learning, computer vision, reinforcement learning without requiring identical keywords. And that's I see that pattern on YouTube a lot because I listen to some bad kind of songs. So sometimes when I just start playing one song, so such songs will keep playing themselves, will keep playing sequentially like that because the system already understands my pattern, the kind of things I like to listen to. Then we have question answering. Suppose the document says Isaac Newton formulated the laws of motion. The user asks, who discovered classical mechanics? Although the word is different, their embeddings are similar. So the model recognizes the relationship and retrieves the correct information. Then we have things like automatic summarization. Suppose a research paper contains 10,000 words. So the model computes contextual embeddings for the document, identifies the most informative sections, and generates a concise summary while preserving the main ideas. So this application is widely used in education, medicine, law, systems, business, and scientific publishing. Then for code generation, imagine programming language also possess context, right? Suppose the programmer writes defines the function square of x and return x multiplied by x and print square. So this model predict that the next token should probably be 5 or another valid expression. So because it understands the surrounding code. So um so the contextual understanding enables AI coding assistance. So that's why sometimes even when you are making mistakes, AI can correct because it understands the context. So for mathematics, now mathematical reasoning also depends on context. Suppose the conversation defines A is 1, 2, 3, 4. Later the user has computes its determinant. So this is the only vector, this is the only matrix you have. So it just computes the determinant of that. So the model understands that it refers to matrix A here. So and then you get the determinant, which is 1 times 4 minus 2 times 3. That is -2 right there. Then for medical artificial intelligence now, medical AI systems analyze patient records using contextual understanding. Example, you have patient history like fever, persistent cough, chest pain, shortness of breath. The combination of symptoms provides much more information than any individual symptom. So contextual embeddings allow AI systems to recognize these relationships. And then you have legal document analysis. So legal contracts often contain references such as the party mentioned in section 2. The AI must determine exactly which entity the party refers to. So attention mechanisms enable the model to connect references across multiple pages of a document. Now we have scientific literature review. Researchers often ask, what have previous studies concluded about transformer models? Large language models can analyze hundreds of research papers, identify common findings rather, and generate concise summaries. So this significantly accelerates literature reviews. So then we have educational tutors now. Educational AI systems use conversational context to personalize explanations. Example, student says, I don't understand derivatives. Later, can you explain it differently? The tutor understands it refers to derivatives, not to another mathematical concept. So this creates a more natural learning experience. Then we talk about the mathematics behind these applications, right? So regardless of the application, the same mathematical pipeline is used. You have input, which is your prompt, then broken down into tokens, the embedded, attention score computed, the context understood, and then the prediction is made. Only the final tasks actually change. So the underlying mathematics remains remarkably similar. So here now, if you have you have a document containing these vectors, and then you have a query here. So the query is multiplied by that, and then you can get the similarities, between them. So you have 0.99949 0.9945 and all that, 0.9995, 0.089. Of course, this one is the biggest. So the document with the highest cosine similarity is considered the most relevant. So that means the second document here is most relevant to the query here. So you have documents, you have the query. So this second one here, 0.999, corresponds with, this one right here, 2017, which is pretty close to this. So a simple recommendation system. Imagine you have linear algebra, machine learning, deep learning, computer vision, and then so the similarity is 0.25, 0.91, and all this. So of course they want to be recommended with 0.91, which is machine learning like that. So you get that machine learning stuff. And then you have so selecting the highest probability prediction, import numpy as NP. So you have positive, neutral, and negative. And then so if you do this now, 0.82 works and you get positive for that. So this simple idea underlines many AI classification systems. Now, why context is the key innovation here? Earlier natural language processing systems relied heavily on keyword matching, manually designed rules, fixed grammatical patterns. So large language models instead learn contextual representation directly from data. This allows them to understand paraphrases, resolve ambiguity, reason across long documents, and answer follow-up questions, and generate coherent human responses. So the ability to represent context mathematically is one of the defining breakthroughs of modern artificial intelligence. So again, we have the key takeaways here. Contextual understanding powers virtual AI. I mean, we've talked about this a lot of times, right? But you can just read through this. All right, so we go on to advantages, limitations, and future directions of context understanding. So ChatGPT represents one of the most significant breakthroughs in artificial intelligence. Its ability to understand context allows it to perform tasks that were previously impossible for traditional natural language processing systems. However, like every AI system, it has both strengths and limitations. Understanding this helps us appreciate what ChatGPT can and cannot do. So, advantages of contextual understanding. Traditional chatbots treated every question independently. For example, my favorite sport is football. Later, user says, who is the greatest player? Traditional chatbot might ask, which sports, right? So ChatGPT instead understands that the context is still about football because the information remains in context. Then better language understanding. Context enables ChatGPT to interpret ambiguous words correctly. Consider I sat by the bank. I mean, we've used this example a lot. Therefore, long range reasoning, we've also talked about that. Attention enables the model to connect words that are far apart. Then improve text generation. Context allows generated text to remain coherent, grammatically correct, and all that. I've talked about semantic understanding. So embeddings capture meaning rather than the exact wording. So no matter how you change words, so artificial intelligence changes education and AI is transforming learning, contains different words. Yeah, their embeddings are very similar. This enables semantic search and intelligent document retrieval. They're multitasking learning. So multitask learning. So the same contextual architecture supports translation, summarization, and all of these things. So no separate model is required for each task in this case. And then you have limitations of context understanding now. So, because despite its impressive capability, ChatGPT has important limitations like finite context window. So, at some point, some tokens will have to be pushed out once the context window is saturated. That's the idea of finite context window. Then there's no permanent memory. Unless additional memory mechanisms are used, the transformer itself does not permanently remember previous conversations. And because context windows are finite, then statistical rather than human understanding. ChatGPT predicts likely tokens using statistical patterns. It does not possess consciousness, emotions, and all of this. Although its responses may appear intelligent, they are generated through probability estimation rather than human reasoning. Then we have hallucinations. So sometimes the model generates information that sounds convincing, but it is incorrect. For example, it may invent references. I mean, we've seen that a lot. If a professor lost his job in Hong Kong because of of references that do not really exist, then fabricate quotations, produce incorrect dates, create fictitious research papers. These errors are called hallucinations. So users should verify important factual information. So that's why when you use AI for anything, you have to own the outcome at the end of the day because AI can give you wrong answers that sound convincing. So sensitivity to prompt quality. Responses depend strongly on the prompts. For example, explain AI may produce a broad overview, whereas explain AI mathematically using linear algebra and probability. Now that makes more sense. Then produces a much more specialized response. So this new one now produce a more specialized response. Better prompts generally produce better output. So it's more like this overall idea of computer, which is garbage in, garbage out. So your prompt determines the quality of answer you get. So the attention mechanism compares tokens with another. For n tokens, standard self-attention performs approximately n squared pairwise tokens. So very long context, therefore, it requires substantially more computation and memory. So for future directions, right, researchers continue improving contextual language models. So several important research areas include longer context windows, more efficient attention mechanisms, better factual accuracy, reduced hallucinations, faster inference, smaller computational requirements, improved multilingual understanding, better reasoning capabilities, and more reliable long-term memory systems. So these advances will make future language models even more capable. So we see the mathematical summary again. You have text turned into tokens and all of that. Like I've given this a couple of times. So even this one, the number of tokens and the pairwise interactions will be square of that. So we have done all of this a couple of times. So you can also, loss of context can also happen here because as you add new words, the first one will go out because here the maximum length is 4. So here, once it saturates at 4, any new word you add is going to push out the first one, push out the next one, and it keeps going like that. So you need to observe how older tokens gradually disappear as the context window fills. So comparison with traditional natural language processing, right? You discover that so traditional natural language processing was rule-based, had rule-based systems. Now, this one, ChatGPT learns from data. This is the transformer-based NLP. Then keyword matching in traditional, then in ChatGPT or transformer-based, it's large context windows. Then you have fixed features for traditional and learned embeddings in ChatGPT. Sequential processing in traditional, you have parallel attention in ChatGPT. Limited adaptability in traditional, you have general purpose AI for ChatGPT. So this comparison highlights why transformer models have revolutionized natural language processing. So, final summary. I mean, this has been a very long one. ChatGPT's contextual understanding is built upon a powerful mathematical framework involving tokenization, embeddings, positional encoding, attention mechanisms, and probabilistic prediction. These components work together to create rich contextual representations that enable coherent conversations, semantic understanding, reasoning across long documents, and a wide variety of AI applications. Although current models have limitations, including finite context windows, computational cost, and occasional factual errors, they represent a major leap forward compared with earlier natural language processing systems. Ongoing research continues to improve efficiency, reasoning, memory, and factual reliability. So, our key takeaways from everything we have been talking about so far is that context enables ChatGPT to generate coherent and relevant responses, and embeddings transform language into mathematical vectors. Then attention identifies the most important relationship between tokens. Context windows determine how much information the model can use at one time, and ChatGPT predicts tokens statistically rather than reasoning like a human. So current limitations are driving active research into the next generation of large language models. So this brings us to the end of this very lengthy video. I don't know how many minutes we end up being. So let me know how helpful this is for you. If there's anything else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead right now and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges you find out. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.